Welcome to Lecture for Research Methods. We'll be talking about how to interpret findings from a simple experiment. So starting off, we can talk about some of the basic requirements defining a simple experiment. First of all, obviously you have an experimental hypothesis that one variable causes changes or differences in another variable. And the one that does the causing, the affecting, is the independent variable, and the one that is affected is the dependent variable. Right? So it's not just that there's a difference or that there's a relationship, but that there's a relationship and that you'll find a difference, and the difference you'll find is one that's caused by a cause-effect relationship. And we actually test that by testing the null hypothesis, which the null hypothesis, in essence, is that there is no cause-effect relationship. Technically, though, it's really just that there's no difference in your variable. No difference in the dependent variable depending on the independent variable. But so that's kind of a technicality, because if there is no difference, then there can be no cause-effect. And notice here, whenever we write the null hypothesis, you have mu1 equals mu2. These are not statistics, but parameters, right? Remember that from statistics. So we're talking about the average in one population is the same as the average in another population. Basically saying that if you have some group of people and you do different things to the two groups, the null hypothesis is that they're not really two different groups, that what you do has no effect, and if it has no effect, then they are the same group, and so they come from the same population. So the population averages will be equivalent. Okay. You also, for a simple experiment, need two equivalent groups of participants, right, to demonstrate cause-effect. You start with two groups that are thought to be equivalent on the dependent variable, generally. And they need to be equivalent at the beginning because we hope that after we've manipulated the independent variable, they'll no longer be equivalent, right? We'll find some difference. And this is our evidence of the effect of an independent variable. And there are multiple ways theoretically that you could achieve equivalent groups, but the accepted way in experimentation is random assignment, right? It's the best way to try to get equivalent groups. Doesn't guarantee that the groups will be equivalent, but makes it more likely than most other methods, especially as the size of your groups, the size of your total sample increases. Right? Okay, so we have these two equivalent groups, and then we're going to do something differently to them. We're going to manipulate an independent variable. We're not just going to look at existing groups. We're going to take groups that are the same and then make them different by manipulating an independent variable. And often, kind of the language we use, we talk about having an experimental group and a control group. So you may designate one group as experimental group, and this is the one that you really do something to. You have kind of the active level of the independent variable. And then the control group, which is probably a more appropriate term, would be comparison group. But this is one that you maybe don't do something to. Like if we want to see look at the effect of hitting someone in the face with a pie. We look at the effect of taking someone's cell phone from them. Right? So the experimental group would get a pie in the face or get their cell phone taken away. The control group would not get a pie in the face, or they would not get their cell phone taken away. So we don't do the thing that we think is going to have an effect on whatever our dependent variable is. And generally, again, it's either kind of a zero level of the independent variable for the control group, or maybe just a low level, right? Because we could have, imagine a simple experiment. Always the simplest thing to think about is usually a drug study. Instead of doing 10 milligrams of drug versus no drug, if the standard dosage that is being given for this drug is already 10 milligrams, then you may conduct an experiment where you say, okay, I want to see what happens if we give twice that. So experimental group may be 20, and the control group may be 10. Right? So again, that's why I say sometimes it's better to think of it as a comparison group, because it's a different level of the independent variable than the other one. Although often it is a zero level where you get no drug, no effect, depending on what you're studying. So we're going to do something differently in the two groups, and then we're going to look at mean differences. Right? To see if the groups differ, we don't typically look at each individual score and compare them one by one. Really, we look at numbers that can summarize the typical score of each group, and that's what an average or a mean does. It's the typical score for a group. Right? And the larger your standard deviation in that group, the less typical that mean is. For smaller standard deviations, then that mean is pretty typical. Right? And our stats take into account how typical the mean is, right? That's where you get that variability, that error variance. It's all kind of think about that being related to standard deviations. Okay, so we're going to look at these the two groups' averages, typical scores, and see if they're different. And when we do, we then need to make a decision, right? Because statistics won't tell you, oh, the null hypothesis is true or false. Stats will only give you some information regarding the probability of getting results that you observed. Okay? Stats will, again, give you information regarding the probability of getting the results that you observed. Right? You must then make a decision based on this information whether or not you feel comfortable, confident enough saying this null hypothesis is not true. Right? If that's the case, the decision you make is to reject the null hypothesis. Right? So then you'll say that the groups came from different populations, that mu1 does not equal mu2, that the two groups really are different, even though they were hypothetically equivalent before I did something to them. Now that I've done something to them, they're from different populations. So if it's a sleep deprivation study where I've deprived one group of sleep for 3 days and the other group I let them sleep as much as they wanted, now one group is from the population of people who get sleep deprived and the other is from the population of people who don't get sleep deprived. And these are different populations now. Okay. The correlate to that is the independent variable had an effect on the dependent variable. And that's typically the decision you want to be able to make. Right? But sometimes you can't. And you end up making your other decision, which is to fail to reject the null hypothesis. And so, obviously, opposite of what we had before. Now we think, well, then the groups came from the same population. So the sleep-deprived people, the non-sleep-deprived people, they're really the same people because sleep deprivation had no effect. Right? The independent variable had no effect on the dependent variable. Okay. Notice here that the language isn't reject the null, accept the null. It's reject the null, fail to reject the null, right? Not accept the null hypothesis. And we never say this, and it has to do with the logic of null hypothesis statistical testing, right? Just because we didn't show that the two groups differed in our experiment doesn't mean that they weren't different. Doesn't mean that the independent variable had no effect, right? It might have been that there was an effect, that they really are different, but the effect wasn't big enough to be observed given how we looked at it, right? And how we looked at it, the problems with that could be related to the sensitivity of your measure, could be related to the amount of individual variability in your groups, could be related to the how strong your manipulation of the independent variable was. There's lots of reasons not to find an effect, but there's so many reasons that we never say, okay, well, this clearly has no effect. All we can say is we failed to find an effect. Okay. So, how do you know when to make which decision? If we look at in the M here is like a x bar, right? Average of the a sample average, sample mean. If they're equal to each other, if two groups scored exactly the same, then that's pretty straightforward. There's no observable effect, right? And we can kind of rewrite that mathematically. Said the same way. M1 minus M2 is equal to 0. But even if the independent variable had no effect, we probably wouldn't get this where the means were exactly equal to that, where if we subtracted one mean from the other, we would get 0. Right? Why is that? Well, random error. Right? So, well, how do we tell how different they need to be about and the difference between the two means, how different it needs to be from 0 to say, okay, they probably really are reliably different. Because a lot of times we'll probably find, well, I mean, if you did the study a billion times, and if it had no effect, a lot of times you would find exactly the same. Sometimes you'd find the difference would be slightly positive, sometimes slightly negative, but it would hover around 0. Right? But how different does it need to be? Well, this is where we get to the central limit theorem, if you remember from your stats classes. And the central limit theorem talks about distributions, right? And one of the distributions it talks about is the distribution of sample means, right? So according to the central limit theorem, if you took an infinite number of samples from some population, right, and calculated means for each of those samples, so imagine that, if your population is Texas A&M University, Texas A&M University, Central Texas, that's your population, and you were measuring IQ, right? And you got a bunch of samples, infinite number of samples, all the samples you can get of sample size 5. 5 people at a time. You got 5 people together. You gave them IQ tests. You calculated an average IQ. Found an average for that group of 5. Got another group of 5. Calculated another average. Got another group of 5. Calculated that average. So you get a bunch of sample means. In whatever the population average is, let's say the population average IQ at our university is 110. Right? Slightly above the population average at large. Because the university expected to be a bit higher. If the population average is truly 110, if I get a sample, some samples I get probably won't be exactly 110. They might be a little lower, they might be a little higher. Right? So I get all these samples, and some might be higher, some might be lower, some might be exactly 110. According to the central limit theorem, if I get a bunch of those sample means, and I take those means, so I got here's a 105, here's a 110, here's a 120, and I put them in a graph, right, from least to greatest. If I do that, if I have an infinite number of samples, and I put all the sample means in a graph, that graph will be normally distributed. Right? And it doesn't matter if IQ is normally distributed in the population in general. It is. But even if it wasn't, the means would still be normally distributed. Right? The idea here again is that most sample means will be close to the population mean, but some will be higher and some will be lower. And it'll be only very few will be a lot higher. You won't have a lot of samples of your 5 people that where the average of that sample is 130. There won't be very many where the average is 70. Maybe 1%. But it might happen. Right? But where the central limit theorem is important is that the fact that this distribution is normal. And because it's normally distributed, we know a lot about the normal curve. And with the normal curve, we can make judgments about probability. If we get some sample mean, we can talk about the probability of that sample mean came from this population. I got these 5 people, and their average IQ was 130. We say, okay, well, are these people really from our university? Because you'd only find a sample mean that size 2% of the time. Right? We know that because of where it falls on the normal curve. Right? How many standard deviations it is above the average. Okay? Which is kind of where you start with the central limit theorem. But then where it really picks up steam is we look at the distribution of sample mean differences. So now we have to extend the logic a little bit by imagining, instead of getting a bunch of samples and putting in calculating means and putting them in a distribution, imagine for our experiment where each group is a sample. And if I calculate the difference between those 2 sample means, okay, then imagine if I did that an infinite number of times. So if I conducted a study an infinite number of times, and I kept getting these 2 group means, sample means, and I calculated a difference between them. Okay, so this was 110, this was 115, the difference is 5. This one was 120, this one was 110, the difference is 10. So all those differences now, I get a bunch of those, put them in a graph. I get the same thing. I get a normally distributed distribution. Right? Now, if the null is true, what should the average of that distribution of differences be? It should be 0, right? Because if the null is true, then they're from the same population. So by and large, those sample means should be the same. So M1 minus M2 most of the time should be 0. Sometimes it would be more, sometimes it would be less. But there would be a normal distribution of those differences if I did the study an infinite number of times. Okay. So again, if the null is true, the average difference between sample means would be 0. Okay. So that means that I'm unlikely to obtain differences far from 0 if the null is true. Okay. Now, if the difference is far enough from 0, it would only be obtained X percentage of the time. Right? So, and this is where you go to your normal curve and you think, okay, what percentage of the scores fall in that area of the graph? Right? And we know that you go up to 2 standard deviations above the mean. You're looking at about 5% of the time where you find scores that are 2 standard deviations above the mean, that big. So if the difference is the difference between sample means is 2 standard deviations above 0, you'd only find it 5% of the time. So that's pretty rare. And so you say, well, when do I reject the null? Well, it depends on some other decision you made, which was setting your alpha level. And your alpha level relates exactly to this distribution. It relates to, okay, if my alpha is 0.05, that 0.05 is referring to the distribution of sample mean differences in terms of how rare do I want it to be to find the difference this big if the null were true. So if my alpha is set at 0.05, right, which you get as a decision I make a priori before I start my study, then whenever I find my differences, I can look at the variability. I can calculate, okay, a difference this big, I would only find 4% of the time. Okay, well, 4%, that's pretty rare. It's rarer than my 5 limit. That's rare enough to say I think it's pretty unlikely that these two sample means came from the same population. Therefore, I think the null is false, and I'm going to reject it. And again, I don't know the null is false, but I'm pretty confident that it's false because it would be rare to find this difference if it were true. Okay. Note, however, that I have italicized here if the null is true. Right? Because this is a conditional probability. Okay? I'm just going to keep that in mind. We'll come back to it in a little bit. Okay. Now, whenever you make a decision, it's possible you could be wrong. And there's different types of errors you can make depending on what decision you make, depending on what is true in reality. And by and large, if you're conscious, you're aware of what decision you make, but you don't ever know what reality is. Right? So we can estimate the probability of making errors, but we can never really be sure if we made an error or not. So a type 1 error, the only time you can make it is if you reject the null. If you fail to reject the null, you can't make a type 1 error. You say, well, geez, if I wanted to avoid those errors, I would just always fail to reject the null. But if you fail to reject the null and you say, oh, there's no difference between two variables, you're not going to get your study published. Because again, you're looking to say this had an effect. But you go through and say, hey, this had no effect, people go, hey, great, we're not going to publish it though because you probably screwed something up. Right? So generally, we want to reject the null. Right? So we want to do that, but if we do that, we might make a type 1 error. And we'll only make a type 1 error if the null, in fact, was true. So in fact, there was no effect, but we said that there was an effect. Okay. So we said this therapy would help people, but we said that this group was different than this group, but in reality, it had no effect. And so even though we had some mean difference, it was the difference was due to some other variable, or could be explained by random variability. We were wrong. We can't ever know for sure that we were wrong. But if people try to replicate our study multiple times and they don't find the same thing we found, then it becomes even more likely that we made a type 1 error. Right? We can kind of look at that in hindsight. So what's the cost of making a type 1 error? If you're talking about a treatment study and you say treatment works, then people will then waste time and money and other resources on some treatment that won't help people. Right? And they could have been using something else that maybe would have worked. And so there's definitely a cost there. Right? And depending on what setting you're talking about, the cost can be of type 1 errors can be greater or lower. But it's not the only thing that is problematic, even though it's the one that for many, many years researchers focused on trying to decrease the likelihood of type 1 errors. We really worried about that. Now people are saying, wait, there's another error you can make too. You got to pay attention to this type 2 error, which type 2 error you can only make if you fail to reject the null. Right? Which generally, we don't want to fail to reject the null, but we might. And if we fail to reject the null, and in fact the null was false, well, that's obviously an error. So in this case, there was an effect, but we said there wasn't. And you might think, oh, that's no harm, no foul, right? You said this treatment really worked. I said, no, I don't think it works. Well, these people aren't going to be going and doing something that doesn't work, but there's still a cost here, right? Now, there's a treatment that works, and people could have been using it. You could have been used to help people get better. I'm talking about some medical interventions maybe to save lives, but it's not being used because you said, oh, it doesn't work. Right? So it has a cost as well. And then people will, again, kind of waste time and resources looking elsewhere for the answer to some problem until maybe they come back and figure out, hey, maybe you'd make a type 2 error there. Okay, so two different types of errors you can make, and the error you make depends on the decision you make, and it depends on what is true of the null hypothesis in reality. So what can you do to reduce the likelihood of making errors? A couple things. For type 1 error, classically, decrease alpha. So make it smaller. So if you have alpha of 0.05 and you go, oh, I'm going to make a type 1 error, I'm going to tighten up. I'm going to make my alpha 0.01. 0.01 is less than 0.05. So now think back to that distribution of sampling mean differences. Now a difference has to be even further out in the tails, right? Has to be even bigger for me to reject the null hypothesis. Okay. So if I make alpha smaller, it makes it harder to reject the null. Only very large mean differences will result in rejection. Okay. If I do that, what's the impact it will have on making a type 2 error? Right? I'm reducing the likelihood of type 1, but I will increase the likelihood of type 2. If I make it really hard to reject the null, well, then I'm less likely to reject it. If I'm less likely to reject it, I'm more likely to make a type 2 error, because that's part of a type 2 error. Right? And then the other thing that's really the only thing you can do statistically, but experimentally, you can decrease the likelihood of type 1 error by designing a good experiment, right? By eliminating confounds. Right? Because remember, type 1 errors, whenever you say you had an effect when there wasn't. Okay. And sometimes you may do that because of random variability, but you might also do it because there's some other variable causing a difference that's not your independent variable. So you have to eliminate all those things that differ between the two groups other than the IV, and those things are called confounds. Right? And then type 2 errors, which when we work to decrease the probability of making a type 2 error, we're working to increase power. Right? Those things are kind of inversely related. To do that, obviously, we would increase alpha. To say, well, I've got an alpha of 0.01, but man, I'm worried about missing something. I'm worried about, I think there's an effect here, but I think it's a small effect. And I think if I use alpha of 0.01, I'm going to miss it. I'm going to say there's no effect when really there is. So I'm going to use a more liberal alpha, a bigger alpha, move it up to 0.05, maybe 0.1. Right? If I do that, though, what am I doing to likelihood type 1 error? I'm increasing the likelihood of type 1 error. So moving alpha has effects on both types of errors. Right? But doing other things, less so does it affect both types of errors. But that one definitely affects both. So other things I can do to increase my power, standardize procedures, right? Work to reduce the impact of random error by exerting strong experimental control. So again, designing a good study makes errors in general less likely. You're more likely to discover the truth that is really there. Okay. Using sensitive and reliable measurements, right? It helps you measure. It helps if your measure can show subtle differences in the dependent variable. Here's where we get to kind of small effect sizes, right? And a lot of times when people talk about studies being underpowered, people focus on, well, you didn't have enough subjects. But it might be a problem with your measurement. If your measure is too crude, too broad, and can't pick up on subtle differences, then you might be missing out on important between-group variability that shows you the effect of your independent variable. Okay. Another trick is to use more homogeneous groups, right? Because the more homogeneous your groups are, in homogeneous groups, by thinking about your whole sample being very homogeneous, everybody's alike, and then randomly assigned to two groups. Doing this reduces within-group variability. It makes it easier to see between groups variability, right? So if you have an animal study and you're looking at rats, well, the easiest thing to do, get a bunch of genetically identical rats. Breed them to be the same, and then you can give one cheese to run the maze and give the other one pizza and see if there's a difference in how fast they run the maze. And now you can be more confident that, well, the differences I see are because of what I did to them, my independent variable, and not due to these other individual variables, because they're all genetically identical. Right? And we can't necessarily find genetically identical people, large groups of them, We can't, not allowed to do cloning yet for psychological studies, but we can find people that are more alike, if we want to, than including more diverse groups. But again, it helps with power. But think about what impact that might have on external validity and generalizability. Right? So there's always costs in all your choices. Obviously, the thing most people talk about, getting a large N, right, helps reduce the impact of random error because the randomness gets more evenly distributed across groups when you have more participants. And the other thing you can do experimentally is use extreme levels of the independent variable. Don't use subtle manipulations. If you want to know about the effect of caffeine on test scores, you don't give one group one soda and then give the other group 2 sodas. You give one group 1 soda and give the other group 10 Red Bulls, and then we see if there's a difference. Right? But again, if I do that, I'm really going to say, okay, does caffeine have an effect? But I wonder, okay, what's my generalizability of that? Because how often people, other than maybe Dr. Yeager, drink 10 Red Bulls in a day? So again, there's not a right and a wrong for a lot of these choices. It's, what are your goals? What are you concerned about? Are you concerned about detecting a subtle effect? Are you worried about people saying that your effect isn't genuine? That you think, I'm going to find one, but people are going to say it's a type 1 error? Are you worried about generalizability? What's your goal with this study? And based on that, you have to make these different decisions. Okay. Now, coming back to what I alluded to earlier about conditional probability. Right? Said, if the null is true, the average difference between sample means would be 0 in a simple experiment. Right? Okay. Conceptually, it's important to kind of try to wrap your head around this. This is a conditional probability because it speaks to whenever you say, okay, the computer spit out this p-value for my t-test, my ANOVA, whatever you ran, and you want to talk about the probability of making a type 1 error. Right? People often want to do that. Or I say, oh, I look at my alpha will tell me the probability of making type 1 error. And it won't. And it won't because the logic is all based on this conditional probability. Okay, so let's kind of walk through some stuff to maybe help you understand that. If you flip a coin, what's the probability of getting heads? Right? It's 50%, 0.5. Right? If you flipped a coin and it was previously heads, what's the probability of getting heads again? Right? And those of you who've taken your math classes and studied your probability will wisely go, aha, it's still 0.5. Because you said so if I flip the coin and I have one result, that result is in the past, it's done, it's in the books. What's the probability of doing it again? It's an independent probability, so it's still 0.5. But if I said, what's the probability of getting heads twice in a row? Which sounds like the same thing as if previously heads, what's the probability of getting heads again? But it's not. It's mathematically different because now probability of heads twice in a row is saying, okay, there's not one flip and it's in the books and it's done. It's saying you've flipped none at all. You're going to flip it twice. What's going to happen? Now it's 0.5 times 0.5, which gives me 25%. Right? So when I have a conditional probability, if this, then this, they're independent probabilities. The two things that are in that sentence. When I don't have the if, and I say what's the probability of two things happening, it's the probability of one multiplied by the probability of the other. Which, because the probabilities are always less than 1, it's always a smaller number than either of the other probabilities. Right? 0.25 is less than 0.5. It's less than the other 0.5. Right? So the probability of making a type 1 error. Okay, well, for a type 1 error to occur, you have an if. It's if the null is true. Right? If the null is true, we would only have found a difference this big this percentage of the time. Right? So when you say that, so let's say you have a p-value of 0.04, right, which is less than your alpha of 0.05, so you reject the null. Yay, the world is good. So if the null was true, I would only find a difference of two groups as big as I found it 4% of the time. Okay, so that's like the sentence up ahead. If previously heads, what's the probability of heads again? 0.5. So that's just the probability of the second half. To know the probability of an error, I have to know the first half of that sentence. The first half of that sentence is if the null is true. So what's the probability that the null is true? Right. I have to know that to know to be able to calculate the actual probability of a type 1 error. Okay. So how do you calculate the probability the null is true? You can't. And there are some statisticians and mathematicians that work on probability talk about ways of estimating that. But we're not going to get into that now because it's a whole separate field of statistics, and one that still isn't the majority of the field. But in general, we don't try to estimate it. We know that it's less than 1, right? It's not 100% that this had no effect. It's probably pretty low. Like if we're designing a study thinking that A affects B, if we're not idiots, it's probably a pretty good chance that it does affect B and that the null is not true. Right? But whatever the probability is, if it's less than 1, then the probability of type 1 error is going to be some number less than 1 multiplied by that other probability you found, multiplied by 0.04, which will make the end result, the probability of type 1 error, less than 0.04. How much less? I don't know, but less. So another thing people confuse them, they think, oh, well, it's alpha, it's p. It's not alpha. The probability of type 1 error is not alpha. It's not p. The probability of type 1 error, in general, if you get a p-value less than alpha, then you can say that the probability of type 1 error is less than alpha. Okay. And to be more precise, it's actually less than your p-value. Right? The p-value sets the maximum probability that you made a type 1 error. Right? Which you may think, wow, well, geez, then that's fantastic. Then there's probably, if I find an effect, it's probably really unlikely that I'm wrong. Yes, but keep in mind, to be right, if I have two groups and I'm doing a drug study, one gets the drug, the other doesn't. For me to be right when I reject the null hypothesis, and I'm measuring depression, for me to be right, if one group's depression score is 97.0 and the other group's score is 97.0000001, if I reject the null hypothesis, I say those two groups are different. If in reality it's 97.0 and 97.00001, then I am right. Yay, rightness. Right. So again, that which is a limitation of null hypothesis statistical testing. It doesn't tell you about the magnitude of the effect, only that there is a difference in the population. Is that difference meaningful? That's a whole other question. Okay. Which is why never, whenever you're reading stuff or you're writing, if you see differences in p-values, this is significant at the 0.05 level, this is significant at the 0.01 level, one isn't more significant than the other. Right? That's an inaccurate statement. That doesn't indicate a bigger effect. And it has to do with these probabilities, which doesn't directly relate to the size of the effect. It's influenced by the size of the effect, but it's also influenced by a lot of other variables, such that you can't talk about something being more significant. It's just a yes/no, depending on what alpha level you set a priori. Is statistically significant? Is not significant. It's not more or less statistically significant. Okay, let's talk about a little bit about the common test you would use for a simple experiment. Probably be a t-test, right? And where, if you remember from stats, basically the t-score is your mean difference divided by some quantification of the variability within groups. So it's another way to think about it is between groups difference divided by within groups difference, right? To where if those were equal, t would be 1. Right. So you usually calculate some t-score, and then you look up in some table a t-critical using degrees of freedom and alpha, and you compare the t-value you obtained to your critical value and make some decision. And those degrees of freedom are related to n, the size of your sample. And this ties back into the central limit theorem, because essential limit theorem is based on having an infinite number of samples, and you only have these 2 samples. Right? So because of that, it says, well, that's still okay, but it's more okay the larger your n is, because the larger your n is, the more the distribution will be normal. The smaller it is, it gets a little funkier shaped. So because the shape differs, the probabilities differ, and that's why you have the chart, and you can't just use a normal table, because the shape of the distribution created depends on what size of sample you use, and that's where the degrees of freedom comes in for t-tests. So you compare t obtained to t critical. If t obtained is bigger than t critical, you reject the null hypothesis. Right? Easy squeezing. So now that you've done that, you've made your decision, and you've said you had a statistically significant difference, and concluded that the independent variable had an effect on the dependent variable, or you said there was not a statistically significant difference, and you concluded that there was insufficient evidence to conclude that the independent variable had an effect on the dependent variable. Now you got some questions. So, first scenario: what if you had non-significant results? And when I say non-significant, I mean not non-important, but not statistically significant. Okay. Now, generally, this is a bad thing for you. You wanted to find a difference, right? That's how you designed your study. So then you got to figure out, well, why did this happen? And you got to think about the likely suspects. First of all, you think, okay, what about size of n? So again, and this should sound very familiar with what we talked about in terms of type 1, type 2 error, right? Especially type 2 error for non-significant results. Maybe I didn't have enough people in my sample. Right? Then I think, okay, how diverse was my sample? Maybe that's a problem. Right? Maybe there was too much variability. I had too diverse of a group, and that's why I didn't find an effect. So really, in the real world, this effect exists. It's just hard to find if you have a lot of diversity in your sample. Maybe something I just kind of screwed up in terms of the design of my study or the execution. So again, maybe the effect was there, but I made some mistake. Right? Maybe the measure I used wasn't very good. I didn't manipulate the independent variable strong enough. Here's the measure. Maybe the measure of my DV wasn't reliable or sensitive enough. So again, this is about maybe reality. In reality, I'm still right. I just didn't show it because of something very specific about the way I looked at the question. Right? Maybe when I tried to manipulate the independent variable, wasn't significant enough. Okay. Now, if you get significant results, generally you celebrate, but you still have to address, well, might I be wrong? Because other people will wonder, might they be wrong? I think they're wrong, and here's why. So you have to think about that before they do, and address those things. So obviously the biggest thing we're thinking about is confounds. You found these two groups were different. Is there any reason to think that they're different, not because you're an independent variable, but because of some other variable? Right? So confounds, and then also the size of the difference is important. So I found a statistically significant difference. Yay! People go, well, how big was it? And you go, well, the p-value is this. And they go, great, how big was it? Well, so you can't talk about the p-value. You got to talk about now about the effect size. And this is a push in the past couple of years in the field to report more than just p-values, to report effect sizes or confidence intervals, so people can get an idea of, okay, really how big was this difference? And an effect size is just a standardized way of calculating the difference so that people can compare two different studies that have different size samples. The effect size standardizes it in terms of the sample size and the variability in those samples. So, okay, here's an effect of 0.2. That's the same effect we found. Or we found a bigger effect or a smaller effect, whatever. Right? So you have two therapies, and both of them work, but one leads to larger effect sizes when measuring the same dependent variable. Well, then maybe that therapy is better. So we want to look at confounds, we look at the size of the effect, and then obviously we want to think about generalizability. Okay, so I found it. Now, does it apply to anybody in any situations that are at all different from the way that I looked at it? Okay. Okay, so that's a fairly quick review of a lot of big ideas related to experimentation set in the context of a simple experiment. If you can understand it in this context, then you can apply it to other contexts as well. Okay. That's all for now. Take care.